Okay, so today we're going to take a look at some microcode for the new improved 2-byte data bus. So remember, we said that one of the primary ways that we can increase the performance is to increase the width of the data bus so that every time we do a memory fetch we get more than just 1 byte of data. And so here in figure 12.17 we looked at this new improved 2-byte system data bus. And remember, what we had to do is, instead of just having one MDR, now we have 2 MDRs, memory data registers, an MDR even and an MDR odd. And the other thing that we had in this figure is a shortcut path so that you could go from the MDR straight to the MAR. And we're going to do an example today that I think will show how the huge increase in performance that we can get by doing that. And then, and remember, we said that anytime the CPU asks for a byte of memory to come from memory, that if it requests a byte from an even address, it always goes into MDR even. So in figure 12.18 here, we said if the CPU requests the byte at 0AB6, the memory system will actually deliver not just 1 byte but 2. And so it'll put the requested byte in MDR even, but then it will put the content of memory location 0AB7 into MDR odd. And so if the CPU asks for the content of 0AB7, well, it'll still just do those 2, like as in this table. Remember that? And then at the very end of class, we said, okay, so here is a picture, a pinout diagram of the 2 memory chips that, for these 2 different size data buses. And we see over here, this is figure 12.19, we see over here in part A, this is the memory chip that you would use, that you would wire into the system bus in the case of a 1-byte data bus, and there are 16 lines, 16 address lines and 8 data lines. And then what was curious about this other one on part B, the chip where we have a 2-byte data bus. How many address lines do we have? We still have 16 lines? Do we still have 16 address lines? No. That was only 15. And why is that? Because we don't need... Yeah, because regardless of whether, according to that table, regardless of whether here, let's go back to the table. Regardless of whether we ask for the byte at 0AB6 or 0AB7, we're going to get the same thing. So why have that address line on the bus? Is
A0 considered even?
Well, A0 is the least significant bit of the address bus. And so if it is 0, it's even, and if it is 1, it's odd. Okay, here, let's do another scenario. Now, all of the examples in this book, and all of the examples that we use, are super tiny examples. So they're not realistic in terms of size, but in terms of concept, the concept is exactly the same. Now let's take a look, let's think about another scenario. In figure 12.19, we have these 2 memory chips, one with a 1 byte with 16 lines, and the other one with 2-byte data that has only 15 lines. Suppose instead of increasing our data bus width from 1 byte to 2 bytes, suppose we increased it from 2 to 4. Now just think about how this would, because it scales, this idea scales. If now 4 bytes, how many bits is that? What's 4 times 8?
30.
That's be 30, so that'd be like a 32-bit data bus. Are you with me? So now, how would this chip be modified? A good question. Can anybody, for sure A0 would be missing. Would A1 and A2 also be missing?
Yeah, because you could access it through A3.
I don't think so. I think you're off by 1. Which addressing lines would be missing?
So just A1.
A0 and A1 would be missing.
So A2 is still there.
And A2 would still be there, right? Because those two missing address lines could access how many bytes? Those two at 0, 0, 0, 0, 0, 0, 1, 1, 0, or 1, 1, so 4. So, but if we get data in chunks of 4, then those two addressing lines would be missing. So we would only have A2 through A15. And how many data lines would be coming out? We just said it a minute ago. 32. There'd be 32 coming out. And what if it were a 64-bit data bus?
64.
There would be 64 data lines, and what addressing lines would be missing?
We'd be missing A0, A1, and A2.
A0, A1, and A2 would be missing. So do you guys see the pattern? And furthermore, let's go back to here. Let's go back to this figure 12.17. If we had a 4-byte data bus, how would this be? Instead of having an MDR even and an MDR odd, what would we have to have? How many MDRs would we need?
4.
4. So we'd have to name them, I don't know, MDR0, MDR1, MDR2, and MDR3. Are you with me? And then we'd have to have more complicated circuitry to be able to extract out 1 byte from those 4 that could come all at one time. But the whole thing, it's like the concept is the same.
Would you need like 2 MAR muxes?
Yeah, well, the thing of it is that now you'd have to choose, well, now do we want to have a shortcut path to go from 0 and 1 into the MAR, or from 2 to 3 to go into the MAR? And so, yeah, all those decisions would have to be made accordingly. Yeah, so that would affect the shortcut paths also. But all of that, that's all just plumbing, and that's what the computer organization engineers do. They weigh all the trade-offs, the space-time trade-offs for increasing the performance. But those are the issues that happen when you increase the size of the data bus. All right. Now, you guys, here comes, let's think about what the ramifications are of this, because there are many. First, what's the von Neumann cycle? Fetch, decode, increment, execute, repeat. Now let's think about fetch. In PEP 9, what do you fetch? Yeah, the instruction specifier, that 1 byte, right? But now, with this increased data bus width, how many bytes can we get in one fell swoop, in one memory access?
2.
We can get 2. So what are we going to do? We're getting more than what we need. But it takes 3 whole cycles to get still. So what should we do with that extra 1? Do you see what I'm saying? Yeah. Once we get it into the CPU, we have those temporary registers. And so we can store it. And here, so here in this slide, we fetch. If PC is even, we fetch the instruction specifier and prefetch the next byte. And we store the prefetched byte in T1. Let's go back and look at remember what T1 is? We have to go all the way back to our figure 12.2. T1, what's the address of register T1?
12.
No, I don't think so.
Oh, wait. 11.
It's 11.
Yeah.
Okay, so that's register 11. So now, because we only need 1 byte, but we're going to get 2 anyway, well, let's save what we got so we don't have to store it again. We don't have to memory read it again.
But that costs a cycle, right?
But yes, but it does cost a cycle. Oh, that's a good point. So what we'll do is we will get both of them, but then we will store the prefetched byte in T1. So storing that extra prefetched one is going to cost an extra cycle. But on the other hand, if the program counter is odd, see, that's what happens if the program counter is even. But if the program counter is odd, what do we know? If the program counter is odd, what do we know? We know that we did a what? That we did a prefetch. Do you see what I mean? If the program counter is odd, we know that we did a prefetch. So therefore, we don't have to do we can just Get it from register T1. And then what does that save us?
2 cycles.
That saves us 2 cycles. So net, on average, we're better off. And now, you guys, what let's do as a group, and we'll go around the room, let us do a fetch under both of these conditions. Are you with me? We're going to do a fetch if the program counter is even, and we'll see how many cycles that takes, and we'll do a fetch if the program counter is odd, and we'll see how many cycles that takes. Now, now, let me just say one thing about this. I wish after we had this all done that I could demo this with the PEP9 app. Unfortunately, the PEP9 app is only out in its beta version now, and you can still use it. The model is implemented correctly, and so you can still write programs for the PEP9 CPU with the 2-byte data bus and run them and make sure that they pass the unit test, but you can't single step because that part of the app is not yet complete. Probably what I'll do is once it gets complete, I'll demo it offline and put it in the lecture anyway. All right, so now let's go ahead and see if we can do, so here's what we're going to do. We'll do this together. We're going to do fetch and increment. Okay, so here it's going to be fetch, increment, assume PC even. Okay, so that's what we'll do together. All right, now maybe what we should do is take a look, have in front of us maybe this figure 12.17. We're going to have to, figure 12.17 doesn't have the register bank, but can you remember the addresses, the register addresses? We said 11 was T1. And do you remember what the, so how do we, okay, so let's do it. Who wants to start? Cycle 1. Wait, when you do, yeah, let's go back and review let's go back and review the von Neumann cycle. The first part of the von Neumann cycle is what? Fetch. And what do you fetch?
Fetch the instruction.
You fetch the instruction
Address, which is in the program counter.
at the memory address that the program counter contains. So how do you do that? You got to take okay, so the program counter contains the address of the instruction to fetch. So what do you have to put where? You got to take the content of the program counter and put it in where? Yeah, it's got to go through, what does it have to go through?
It's got to go to memory, right? The MAR line.
It's got to go in the MAR, MARA and MARB. Okay, so is everybody clear? So up here, so we got to take what's in the program counter and put it in the memory address register. Okay, so now how do we do that with this new setup? Do you remember the address of the program counter?
It's 4 and 5.
Is it 4 and 5?
I thought it was 6, 7.
Oh, now do you think it was 6, 7? Yeah, but see, we're going to have to verify this. Okay, back to 12.2. The program counter is where? 6 and 7. Are we good? The program counter is, so we have to remember that. Program counter is 6 and 7, and the temporary register is 11. And we want to bring the instruction into the IR, right? Which is register what? 8. So we got to remember those addresses. Can you help me remember those? I will forget, I'm sure. So see if you can help me remember that. So here we will have this figure in front of us, 12.17. All right, so now what do we have to put where? Program counter into the MAR. Good. Okay, so how do we get the program counter in the MAR? Who wants to start?
A equals 7.
Well, A and B. I mean, one's going to go on A and one's going to go on B.
6 and 7.
I think 6 into A, right?
Yeah.
So A equals 6, then what? B equals 7, good. And now that's on the A bus and B bus, but now we have a little extra channel. We have a little extra thing we have to go through. Do you remember? Now what does it have to go through? It's got to go through the MAR mux. So how does the MAR mux work? I think that's correct. So MAR mux equals 1. So MAR mux equals 1. And now what are we ready to do? Yes, clock it in. Is everybody good? And now how many cycles do we have to do? We have to do 3 memread cycles. So let's just do the memread cycle. We'll go back and do some parallelism later. Okay, so this will be, now at the end of the third memread, we know that what is where? We know that those
2 bytes of data are in
two
the data bus.
are on the data bus, yes.
So we can clock it in. We can clock those bytes in.
And we can clock them both in at the same time. So how do we clock it? So what do we have to present to the MDR even? We have to say what? How do we get from what's coming from the bus to be presented as input to the MDR even? MDR E mux is 0. And what else did you say?
MDRO mux
Also
is also
0. MDRO mux, is everybody following this? Also equals 0. Are we good? And now both of those are being presented to the MDR even and MDR odd. So now, exactly. And we can put them in at the same time in this one cycle. MDR ECK, MDR OCK. All right. And then here what we'll do is we will increment program counter by 1. Well, let's go ahead and do that. All right. So now, when we increment the program counter by 1, we got to start with we're going to have to know the address of the 1 constant register and the 0 constant register.
I think it's 23 is 1,
Oh.
22 is 0.
Oh, nice, nice. Okay. I won't have to flip back. Okay, so how do we do that? A equals 6. So is A equals 6, is that the least significant byte?
Oh, shoot, it's A equals 7.
It's 7. We got to do the least significant byte first. So A equals 7. Now how do we run it through? Oh, and what about B?
B equals 23.
23, you know that is 1 constant. You guys agree? Okay, and then what?
ALE.
Run it through A mux, run it through the AL, yeah, okay, so A mux equals 1. Oh, you guys are good microprogrammers. And now do you remember the function of the ALU? It's 1, I think you're right. It is 1. C mux is 1. So C equals 7, put it back here. Yeah, so C equals 7. And then are we ready to clock? And we have to clock the shadow carry. And we also have to load CK. Everybody clear on this? Now this one should be easy. So this next one is what? B equals 6. Oh wait, let's start with A. Yeah,
A equals 6, B equals 20.
yeah. A equals 6, B equals 22. Okay. ALU.
0.
Is it? I think 0 sends A straight through.
Oh, yeah, you need the shadow.
2 adds the shadow carry. But if we're going to add the shadow carry,
We got to set the CS mux.
yeah, we got to set the CS mux to what?
1.
CS mux equals 1. And then, now coming through, yes, C mux, oh, you guys are good. Is 1, C equals 6, semicolon, load CK, I think. All right? So far, so good, I hope. All right. And now, you know, we would be done before, but now we're going to tack on this little extra cycle. We're going to put that, oh, wait a minute. we're not done yet, because at the end of cycle 4, we have those 2 bytes in the MDR even and MDR odd. Now, which one goes where? This whole thing was under the assumption that what? This whole thing was under the assumption that in the beginning PC was even. So which one? Well, before we do the control lines, what do we want to send where? Not the index register. We want to send MDR even into the, it does start with an I, into the instruction register, right? The first byte of the instruction register. So, and that's even, MDR even. So now how do we route that through? So now what, so there it is in MDR even, so it has to go through the what? The EOMUX. So in line 5, we do EOMUX what? 0 to take it from the left, which takes it from the MDR even, and then it has to go through where? Yeah, see how easy this is? This is not hard at all. You just look at it going through. You just route it through. It's pretty slick, huh? You just, oh, I want it to go here. Oh, go here. Turn left, turn right. Da, da, da. You see what I'm saying? You just, it's just plumbing. All right, AMUX is 0, and then what? Yeah, that sends it straight through. ALU gets 0. ALU gets 0, sends it straight through. Then what?
CMUX gets 1.
CMUX equals 1. And now is it being presented?
C equals 8.
Oh, right, C equals, oh, is 8 the,
I think that was kind of a guess.
okay, that's the instruction register, the first byte, okay. And then what? Ah, cool, huh? And now we're going to tack on this extra cycle, because now we prefetched. Actually, this is an important concept. Basically, well, we'll see when we start talking about caches that this is what a cache does. It prefetches, and it's the same principle. We're going to save time because we cached this extra byte. So look. So now so how do we? So now where is it? It's in. We've got to send what to where now? From MDR odd to where? To T1. Yes. So let's trace it through. So how do we get it from MDR odd to T1? EOMUX equals 1, AMUX equals 0, then what? ALU equals 0, then what? CMUX equals 1, then what? It's 8, 9, and 10 for the IR, and then 11, yeah. C equals 11, and then what? Load CK. Let's see if we did it right. Here is figure 12.20. Somebody check us out here. It should be exactly identical, I hope. Are we good? Well, this actually cost us an extra cycle.
That one did?
Well, I mean, if you look at the fetch with the 1 byte data bus, it was basically the same as 1 through 5. But now what we're doing is we're tacking on an extra one. So this actually takes 1 cycle longer. But that's because we assumed that PC was even. If we assume that PC is odd, now let's do it assuming PC is odd. Okay, so this is up there, so we'll erase it. So check this out. Assume PC is odd. Now, you guys, we don't have to do a memory read. We have to remember. So now what do you have to move from where to where? From register T1 to what? To the instruction register. So, and the address of T1 is what? 11, and the address of the instruction registers is 8. So now how do we do it? Watch this, boom, 1. So A equals 11. So now what? Go through what? AMUX equals 1. ALU equals 0. Send it straight through. CMUX equals 1. C equals 8. And do what? Yeah. That's it. No memory read. Well, we do have to increment PC by 1. So 2, 3. So, but now it's only 3 cycles, and the original was what? 5. So you see, and here's, let's take a look. Let's make sure we did it right. Here, did we do it right? A equals 11, base 2. Yeah. Did you have a question?
Like a break or something there?
Yeah, now that is a really good question. So here's, in order for this, well, wherever the program counter is, it's the address of the instruction to be executed next. So you see what I'm saying? So this works. But here is, let's think about the ramifications of this. This has some pretty significant, and this is really important, you guys. There are alignment issues here, because all we're doing here is we're talking about fetching an instruction. But what other things do we have to get from memory during the execution of a typical program? Not just the instructions, but also what? Well, I mean, what in an assembly language program, there's two kinds of bits. In a machine language program, there's two kinds of bits. Some bits are what and some bits are what? Some are instructions and some are data. Are you with me? You see what I'm saying? There's data. Now look, so in order for this to work, let's take a look at figure 12.22. In order for this in order for us to actually increase our performance, we have to be very careful now. So it comes, you know, increasing the width of the data bus has ramifications here. Because if we're not careful, we're going to make things worse off. Now look, in figure 12.22 part A, this is actually the first part of a program from an earlier section of the book. Do you remember when we did examples, like we had an example with bonus and exam 1 and exam 2 and score? Remember that? And here, bonus was a constant, and so here it's dot equate 10. And look, exam 1 is dot block 2, exam 2 is dot block 2, score is dot block 2, and the first instruction was branch to main. Are you with me on this? So, you know, we would do, you know, branch to main. And now when we get to main, what instruction is executing in main? It's decimal input what? Exam 1 direct. But now look, what's the address of exam 1? It's at 003, and then exam, well, how many bytes is exam 1? It's 2 bytes. In order for us to be able to do this efficiently, we would like, we want to get the 2 bytes of exam 1 in one memory access. But what's the problem? It's at 0003. So if we ask for, if we do a decimal input from 0003, we also have, we get 002 and 0003. So then we're going to have to get 0002 and 003 and discard the 0002, and then do it again and get 0003 and 0004 and 0005 and discard the 0005. Because it's you know, here's the thing. Look, it's like this. Look, you guys. It's like memory is like this. Okay? And if this is 0000, this is 0001, this is 0002, this is 0003, this is 0004, this is 0005, this is 0006. And the problem is, in part A, exam 1 is at 0003, and it's like, it's here, right? Here's where the data is, but the problem is we get chunks. Where do we get our chunks? We get our chunks like this. We can get this chunk, or we can get this chunk, or we can get this chunk. In other words, we get chunks at addresses that are divisible by 2. So this is not aligned. In order for it to be efficient, what do we have to do?
Align with either 002 or 0004.
Yeah, and so obviously if we can't align it with something went before, because that it'll clobber that. So what we want to do is we want to shift this down to align it so that it will be at an even address. Now, and to do that, there is a very common assembly language directive called .align. And .align is actually implemented in the PEP9 assembler. And notice that in part B, with data alignment, what you say is, before you do exam 1, you say align 2. Now, align 2 does not always insert a byte of zeros. It will only insert a byte of zeros if what? If the dot align is at a what address? Is at an odd address. If you throw in a dot align and you're already at an even address, it doesn't need to insert anything. Do you see what I mean? And what that does is that will shift this so that it will be aligned so that you can have those 2 bytes in one chunk. That is the alignment issue. Yeah.
So what if
That's a very good point. So now if you do a dot block 1, like a character, like an ASCII character, yeah, that's very common. So in order to, and then if you had like a dot block 2 and a dot block 1 and a dot block 2, for efficiency you would align the character, or you would align the next data so that all the data is aligned.
So you have to run, or you have to build the program and see where it'll be in memory before you decide to put in the line or not.
Yeah, well, here's the thing. A good question. First, what's the fundamental question of computer science? What can be automated? So the compiler will sprinkle in the aligns. But you are right, it has to be done in order to have the performance. This is a really big deal. But that's what alignment is. Alignment is because when you have a multiple bytes in the data bus and you get them in a whole chunk, you want to have your data. You don't want to have to get part of it in one memory access and then part of it in another memory access. And furthermore, this generalizes the generalization that we said before. What if instead of having a 2-byte data bus, you had a 4-byte data bus? Then instead of throwing in an align 2, you'd throw in an align 4. And that would pad enough zeros to make the next address be an address that is what? Not just even, but what? Divisible by 4. And so the common aligns are align 2, align 4, and align 8. Align 8, if you do align 8, that's 8 bytes, every 8 bytes. And how many bits is 8 bytes? 64. So that'd be like a 64-bit computer. A computer that has a 64-bit data bus. And it would align to the ones that it would pad however much it needs to, and to make the next address be at an address that's divisible by 64. And so, yeah, and so that you see how that memory what that memory alignment issue is. Yeah. So it's not so. Yeah. So that's a big deal. Now. Oh shoot, I wanted to have enough time to do this, but I don't think we do. Watch this, you guys. Do you remember that load index register using indirect addressing? Do you remember when we did that? Here, let's go back. Let's go back and look at that.
It loads the address?
It's the address of the address. Do you remember that?
Yeah.
That was really complicated. Here, let's bring this slide up. There's this, oh here, figure 12.13. Do you remember this? Figure 12.13? I think we only got halfway through it because it was getting so tedious. Okay, so this is load index register assuming indirect addressing. So the operand specifier contains the address of the operand. And remember we had this, look at figure 12.13. we said, okay, in cycles 1 through 5, or this byte, this byte, this byte, this byte, cycles, and remember, it had 18 cycles. But now look, if we assume that everything is aligned, and we have a 2-byte data bus, and we have our little shortcut path. So let's do, here, let's do load. So this is load word accumulator, this, n, indirect. Now what we're going to do is we're going to assume indirect addressing, and we are going to assume that everything is aligned. All right, like we said, like we just discussed. All right, now let's see. Now let's go back to our figure here and see if we can do it. Here's figure 12.17. Now, can you see how to do this? It's load word. So are we doing memory reads or memory writes? Memory read, because we're going from memory to the CPU. So now, where is the address? First, we have to get the address. So the operand specifier contains the address of the address. So what do we have? We have to get the operand specifier where?
Onto the memory address registry.
Yes. Yes, we have to get the operand specifier into the MAR. Okay, so how do we do that?
A gets 9, and B gets 10.
Oh, you guys are cooking. And it's got to go through the MAR mux, so MAR mux equals 1. Oh man, you guys are good. Semicolon, MARCK, right? And now we can get the whole, so now how do we get both bytes? Do 3 memory reads, yeah. We don't have to add 1 to anything. We're getting the whole, so 3 memories. So mem read, mem read, mem read. And at the end of this mem read, what do we know is where? The data is on the system bus, and we need to get them both into where? MDRs. So how do we get them both into the MDRs?
MDR Emux gets 0, MDR Omux gets 0.
MDR Emux is 0. MDR Omux is 0. And clock them both in, so what? MDR ECK and MDR OCK, right? And now you guys, what? Now check this out. This is so cool. Now what?
Mux equals 0.
MAR mux equals 0. So that's going to present them whoosh, to the what? To the MAR, and then do what? MARCK. Look at this. And now that that's in the MARCK, what do we do? 3 mem reads. Are you with me? 6, 7, 8. And at this third mem read, what do we know? MDRE Emux equals 0. MDRO mux equals 0. And clock them both. MDRECK. My gosh, you guys are good. MDRECK. MDROCK. All right. And now we're loading, was that load word accumulator or was that load word index register? Was it accumulator? And so now we can do, but now it's going to take what? Now we got to do 1 byte at a time from the MDR. It's time for us to leave, so let's just see if check out our code here. So 9 and 10. So here it is in figure 12.23. Did we do it right? I mean, 9 and 10 is, yeah? Is everybody, are we good? And like I said, and so here's our result. Our result is that the 1 byte data bus takes 18 cycles, the 2 byte data bus takes 10 cycles, 18 minus 10 is 8. That's how many cycles saved. So the time saving is 8 divided by 18, which is 44%. That's huge. Yeah? Now, unfortunately, like I say, you have an assignment, your assignment for Thursday, for Monday, it was to do a couple of instructions with the 1-byte data bus. And now you're going to redo those with the 2-byte data bus. Unfortunately, you can't see the data flow, but you can check, the unit tests, it'll pass the unit test if you do it correctly. And then you can calculate the savings like this. Yeah? All right. Good deal. See you next time.